Hi guys, I'm Talha Kamran and today I'll present my project which is about implementation of CNN, ARIMA and LSTM machine learning models for solar forecasting and load forecasting. So the main idea and motivation behind it was that solar forecasting and load forecasting, they have a vital role in decision making process for energy consumption and generation of solar powered homes with smart systems enabled. So they basically help in energy harvesting. But the main issue with these things is that predicting them accurately is a challenge because the energy consumption and generation is always varying. So although there are many solar forecasting and demand side management techniques that have predicted energy for larger systems, but the challenge is to predict energy for just a house and then optimize it to get a useful energy output. When I reviewed the literature, so these three papers helped me a lot. And so the first one, it presents a novel approach for choosing the suitable time period for PV power forecasting using an LSTM deep learning model. The second paper that I've mentioned, it presents a comparison of different machine learning models for predicting hourly global horizontal irradiance. And the third one, it presents an implementation of ARIMA and LSTM for load forecasting. So the machine learning models that I used and reviewed were these three, and so the full form is autoregressive integrated moving average ARIMA model, and long short-term memory networks LSTM, and a convolutional neural networks CNN. These three are very famous machine learning or deep learning models. So ARIMA is famous for short-term prediction, and LSTM works best when there's a time series data. And the CNN model is very useful because it doesn't require much pre-processing and it also has the lowest computational time. So after reviewing the literature and selecting the machine learning models, I implemented it for solar forecasting and load forecasting. So load forecasting is also called demand side management, so I'll use these terms interchangeably. So first up is solar forecasting, which is basically predicting solar power generation. So by predicting solar power generation, I mean that I'll predict the global horizontal irradiance. So global horizontal irradiance decides how much energy will be generated. So the dataset that I used for this purpose was from my previous university, NUST, in Pakistan, and it consisted of all the weather parameters needed, and it was recorded from October 2014 to April 2017 with 132,000 data points. So the dataset is shown in the figure on your right. So the pre-processing was done by first reading the CSV file and then converting the date-time column into a usable format. So it's basically string form to number form. Then the dataset was split into 70% training, 20% validation, and 10% test dataset. Then the data was normalized through mean normalization. It helps get better results. And then there was data windowing and input labels were inserted, and then finally the machine learning models were implemented. So the mean normalization of all the weather parameters is shown on the figure. So by implementing and then comparing all the models, so this was the results that we got by model comparison. So for solar forecasting, our models were baseline, linear, dense, CNN, ARIMA, and LSTM. So baseline and linear and these dense models, they are very basic models and they are just there for comparing if we are getting better results from deep learning or machine learning models like ARIMA and LSTM and CNN. So the mean absolute errors of all these models are shown in the second paragraph. So as you can see that LSTM and CNN performs the best. So with only 0.14 and 0.1409 watt per meter square was the mean absolute error. And the computational time was lowest for CNN with only 11.17 seconds. And as when you compare it to the ARIMA and LSTM, that's very less. So as expected, CNN performed best in the case of computational time. So the next up is the load forecasting or demand side management, which is to predict the power consumption. So in my case, I predicted a week ahead forecast And the dataset that I used for this purpose was of an energy consumption of a house in Arizona, USA. And it had 4 years of power values recorded from 2006 to 2010 with almost 1 million data points. So that was a lot of data points. And it was a minute-wise data. So first it was converted to a daily dataset, which I'll explain in the next slide. In the figure on your right, you can see the power parameters like global active power and reactive power, and also the 4 submetering values, as the dataset was recorded inside a house but at 4 different places like a laundry room, kitchen, and bedrooms. So the main challenge was pre-processing of all this data. First, it was only available in a TXT file, so it was converted to a usable format in a CSV file. Then the minute-wise data was added to a daily dataset. So then it consisted of 1442 days of data. But there were a lot of missing values in this dataset. So these were inserted by using the value of previous day. So around 1.25% values were missing. Then the dataset was split into 70% training and 30% test dataset, which is around 159 weeks and 46 weeks. And then windows of weeks of data was made and the machine learning models were applied. And as you can see in the figure on your right, the minute-wise data has been converted to a daily dataset. And also the ACF and PACF plots for ARIMA models are shown. So after performing and implementing different machine learning models like ARIMA and LSTM, the dataset was trained on these models, and then the root mean square errors were calculated. So for ARIMA it was 0.381 kilowatt, while for LSTM it was 0.401. So ARIMA performed slightly better than LSTM, and the computational times were 31.64 seconds and 30.19 seconds for ARIMA and LSTM respectively. So LSTM performed slightly better and had a slightly better computational time, but they almost performed almost the same. And the results are shown in the figures on your right. Here I want to mention one thing, that 0.381 and 0.401 kilowatt RMS error are a mean error for the whole week. But in the figures on your right, you can also see the error for all the Sundays, all Mondays, and every day of the week. As you can see, the error is very less for a Friday, but is higher for a Saturday. So this could be because on Saturdays the power consumption is usually higher than on a Friday, and so that's why it's harder to predict what the power consumption would be on a Saturday. And these were all the libraries and tools that I used for this purpose. So the main ones are TensorFlow, Keras, and Pandas. So just to quickly go through all the libraries that I've used. So I used TensorFlow for generating windows from training, evaluation, and test datasets. And then Keras was basically used for developing and evaluating deep learning models. It has all the models available. And then Pandas was used for reading and manipulating with CSV files, and also for the resample function, which grouped data into days data. And then NumPy was used for array manipulation and splitting the dataset. And Matplotlib was used for making plots and adding titles and different attributes to the plots. Seaborn is based on Matplotlib, and it makes the graphs look better. And then stats models were used for importing ACF and PACF plots for the ARIMA model. So this was only needed for ARIMA model. And sklearn was also another library that I used for error calculation and also for time calculation, and it was very easy to use the functions that were available on sklearn. So now I'll get to the results. So it consists of 2 parts. First is the solar GHI prediction by CNN and LSTM, and then the week ahead power consumption forecast by ARIMA. So in the figure on your right, you can see the GHI prediction by LSTM for 24th March to 26th March. So as you can see, 2 dotted versions. So one is the prediction, and it is compared with the test dataset. As you can see, LSTM provided consistent results, and the prediction are very close to actual values. And then the next figure is for CNN, and it's for the same time period from 24 March to 26 March. And as you can see that the mean absolute error is almost the same so it usually stays very close to the actual values, but the computational time was very less in the case of CNN. So on the figure on your right, you can see the load forecasting results by ARIMA model, and these are the predictions for a full week from 3rd January to 9th January. And as you can see, the ARIMA model, as it performs slightly better than LSTM, but the results show that the predictions for Wednesday and Friday are very close to the actual power consumption, but it's less accurate for a Sunday. So this is actually a major hurdle in predicting power consumption, because there's no set pattern for, or a specific pattern for power consumption. It varies very quickly, but still these predictions are very good and are usable for different purposes, like for designing a home solar power system. And people can use this dataset for reducing their daily power consumption, as they will have the insight of next week or a week ahead power consumption forecast. So in conclusion, I would say that the results show that these machine learning algorithms are effective and can be used by smart home systems or by smart home system companies to implement it in different houses and to minimize energy wastage and maximize energy utilization. So I just point out that the best computational time and minimum error was achieved by LSTM for load forecasting and CNN for solar forecasting. So some of the future works include new deep learning models. So they could be implemented and they may have slightly better computational time, or maybe some new algorithms are being made that works better on small datasets, because right now most of the algorithms works better for larger datasets. So that could be a future work. So if you have any questions, you can write them in the comment section, and thank you for your time.